our last topic for this unit is redox chemistry. And this is the topic that feels a little bit like it doesn't fit. And I can kind of rationalize why they put it here, just in the sense that redox chemistry has to do with movement of electrons between some things and some other things. And since we've been dealing with everything, all valence electron type stuff, I think redox chemistry gets kind of dropped in here because it sort of fits with that overall theme of we've been working with electrons. But it does kind of take us a little bit back to the chemical reactions side of all of this. 101 takes a very, very quick, very shallow look at redox chemistry. The goal is to basically have you set up with some familiarity with the topic, kind of leading into being able to do some biochemistry. And if you're in AP Bio this year, you're going to notice that there are some ideas that seem to cross over from here that you may have come upon in AP Bio or which may come up in the next month or so in AP Bio. If you came through Chem Study, we did do a little bit of this in Chem Study as well, and so some parts and pieces of this are going to look familiar. But it's a very quick, just kind of over-the-top look at redox chemistry. At its most complex level, this gets involved at kind of the biological side of things. Photosynthesis is all about moving electrons. Metabolism is all about moving electrons. The ADP, ATP cycles in biology are all about moving electrons as very complicated examples. We're going to start really, really simple because it's a lot easier to see. I'm going to take just a little coiled wire of copper. So this is just plain old copper, copper solid. I'm going to stick that into a graduated cylinder full of this silver nitrate solution. Silver nitrate is a clear colorless solution. So we're just going to put it down in there. And so what we basically have is this little springy thing in a clear colorless solution. And it's going to take a little while for the chemical reaction to happen. It's not an instantaneous one. So we're going to draw some pictures and then we're going to check back in with how our reaction is progressing. We'll just set that right there and let that run. We're going to go back to some of the particle level pictures like we drew in your first year chemistry class. So my piece of copper is just copper atoms. Okay, anytime you see a solid metal, it consists of just atoms of that metal. And remember, we kind of used that boundary there to show that it's in its solid state. And since we're thinking about electrons, we're going to do a proton and electron count on this copper. Because it's copper, and copper is element number 29 on the periodic table, our copper has 29 protons. And because it's just copper atoms, 29 electrons. Our other player here is silver nitrate. Silver nitrate is an ionic compound consisting of silver ions and nitrate ions. So the silver in the silver nitrate is actually silver with a 1 positive charge. Silver, in terms of protons, is element number 47. And because it has a +1 charge, it's missing an electron, so it only has 46 electrons. You probably recognize this as being a single replacement reaction from our types of reactions in our first unit. We know that the copper is going to come over, it's going to push on the silver is going to get ejected from the compound in the form of a single replacement reaction. So we have our solid copper. We know that aqueous ionic compounds break up into their parts when they're in water. So my 2 silver nitrates are actually a free-floating silver ion and a free-floating nitrate ion. And we learned last year in your other chemistry class that when we need to do those polyatomic ions, we put them in square brackets. But now you've been through the Lewis structure process, and you kind of understand where that comes from with those square brackets. And there's two of them. So here's another silver ion, and here's another nitrate ion. Again, separated from one another because they're an ionic compound in water. You hopefully also remember that when we wanted to do solutions in our drawings, we used this little kind of V-shaped thing to represent our water molecules. And now that you've done some building of models and some talking about molecular shape, it probably makes even more sense to you why we would represent a water molecule as a little bent thing, because water is a bent molecule. So we'll stick some water molecules in here to represent the water that the silver nitrate has been dissolved in. Now, if we revisit our little graduated cylinder here, you can see that two things are happening. The wire is getting fuzzy, and that's the formation of silver on the surface of that wire, and the solution is turning blue. Anytime a solution turns blue, that's a sign that we've got some copper ions present. It wouldn't be good for you or Casey. So as we look at our graduated cylinder with the reaction in it, we can definitely see the appearance of plain old silver, just the solid kind, and the blue color is telling us that we have some copper ions present, which tells us that this copper has now become copper ions, and maybe we'll draw them pale blue here to represent the fact that copper ions give things kind of a pale blue color. Our silver is coming together and actually looks like silver now because it's no longer silver ions, it's silver atoms. So there's our solid silver that's forming. And the nitrate is just kind of along for the ride. Its actual name is a spectator ion because it was here, but it didn't really participate much in the reaction. But we do still have two nitrate ions in there. There's one of them. We'll stick the other one down here. There's the other one. And then we just need the water it's all dissolved in. 1, 2, 3, 4, 5, 6, 7, 8. Nothing magical about the 8 other than I have to have as many now as what I had when I started. And there's our new situation. As we've done this, our silver has gone back to just being a metal. It has its 47 protons, and after the chemical reaction, it's got 47 electrons to go with it. That's how it lost its positive charge. My other product is copper 2 nitrate. So here we've got a copper 2 plus, NO3 minus, NO3 minus. Okay, so that means that my copper still has its 29 protons. But electrons, it's now got a positive 2 charge, so our electrons are down to only 27. So in the process of this single replacement reaction taking place, the copper gave up 2 electrons, and each silver gained 1. What that means is that when this reaction occurred, an electron left copper and went to that silver ion, and another electron left this copper and went to that silver ion, and as a result, the copper is now 2 electrons short, giving it a positive 2 charge, and my silvers are now atoms instead of ions. That's the definition of a redox reaction. It's short for reduction and oxidation, and it represents the movement of electrons from one thing to another. Yeah?
Is the positive charge on the silver what pulls those electrons to it instead of, like, say, going to the nitrate?
Yes, yes. The electrons aren't going to go toward the nitrate because it's negatively charged. They're going to go toward the silver because it's positively charged. Yeah. Now, if we want to think just about the business end of this reaction, Emerson,
Why don't the electrons add up?
they do add up. Why do you think they don't add up? And maybe you forgot to take into account that there's two of the silvers and two of the silver ions. So it kind of looks like it doesn't add up, but it does if we take into account having the double of the silver. That's a good point. Okay, so from the perspective of what we call the net ionic equation, the picture of what really happened, if you look at the nitrates, they weren't really a part of what was going on. Like, they were around, but they didn't do anything. So a simpler version of this reaction would be to say that the copper reacted with two silver ions to produce two silver atoms and a copper ion. And that would kind of get the nitrate out of the way and make it a little bit easier to see what's actually going on here. And then we can look at the story from the perspective of the silver, and we can look at the story from the perspective of the copper and figure out where the electrons are coming from and where they're going. From the perspective of just the copper, this reaction involves copper turning into a copper 2 positive ion because it gave off 2 electrons. From the perspective of the silver, this involved 2 silver ions picking up 2 electrons and turning into 2 silver atoms. But the two processes have to happen at the same time because there has to be a source for these electrons. The source for the electrons is that they came off of the copper and then they traveled over and they joined up with the silver. So this really involved the movement of 2 electrons, and those 2 electrons moved from copper to silver. These single replacement reactions represent the easiest way to see movement of electrons in reactions. There are other more complicated situations where electrons are moving, but this is the simplest possible situation because we can really see the changing of the charges, the moving of the electrons, and how the electrons would have to be involved in the changing of the charges. This type of reaction is called an oxidation reduction, or for short, a redox reaction. It's a reaction that involves transfer of electrons. The first possible way that we can recognize a redox reaction, if you look at your reaction and the charges change, right away, that's your clue that you've got a redox reaction. And that's at its most simple level. The two things going on here are oxidation, which represents a loss of electrons, and reduction, which represents a gain of electrons. If something loses electrons, the way you're going to recognize this is that the charge increases. So in the case of our copper, we went from copper to copper 2 positive plus 2 electrons. So we can see that the electrons are lost. They fell off the copper over to here, but we can also see that that causes the charge to increase. The copper goes from no charge to a 2 positive charge. And so we can recognize that loss of electrons because of the change in charge. From the perspective of the silver was being reduced. It gained electrons. A gain of electrons means that the charge decreases. So from the perspective of our silver, we had, and we'll just do it on a single silver level, a silver ion gained an electron and became just plain old silver. And so you can see that the electron was being gained, but you can also see we went from 1 positive for a charge down to 0. And it's important to remember that when you have just a plain old element, that element doesn't have any charge. And that's why we say that the silver has no charge, and that's why we say that the copper has no charge. In terms of remembering which one is a loss of electrons and which one is a gain of electrons, we're actually going to use a picture to help us. What's that? Cat. Good. Kind of a grumpy looking one. Didn't come out great. What's that? Lion. Good. It's not a cat flower. That is supposed to be a lion, and like I said, kind of a grumpy one at that. If I had a lion, due to my lack of creativity, I would probably call him Leo. And also because that would help me do my chemistry. Loss, electrons, oxidation. And when Leo comes down for breakfast, because he's a house lion and he doesn't want to roar and shake everything in the house, instead of roaring, Leo comes in and he just says, "Grr, it's time for breakfast." And that also reminds me that a gain of electrons is reduction. So Leo the lion says grr. And that's how we're going to remember loss of electrons oxidation, gain of electrons reduction. Some textbooks do oil rig. Oxidation is loss, reduction is gain. My oil rig picture is even more pathetic than my lion picture, so I have to do Leo the lion says grr when I get people to do this. This is useful when we look at reactions like these, where we can very clearly see the ionic compounds, and because they're ionic compounds, we can track the charges. If I go through and assign charges to everything here, I can figure out what's being oxidized and what's being reduced. So my chlorine always has a 1 negative charge. Iron as a transition metal is variable, but if there's 3 chlorines with an iron, that's going to be an iron 3+. The magnesium is just good old solid magnesium. Any kind of metal that's just a plain old metal has no charge at all. When we get to the other side, the magnesium has joined the compound, and the iron has no charge, and it's now by itself. So the first thing you have to decide is whether these reactions are redox reactions or not. If you look down here and anything experiences a change in charge, that's telling you this is a redox reaction. And then we can go one step further and we can think about what actually happened and try to decide what's been oxidized and what's been reduced. Well, if I look at my situation, iron went from 3+ to 0. So the things that were going on here is iron 3+ turned into iron, and it did so by gaining 3 electrons. So that's the GR part of this. So we could say iron is reduced. Or we can look at it from the charge perspective 3 plus down to 0 is a reduction in charge, still making the argument that iron is reduced. From magnesium's perspective, magnesium turned into magnesium 2 plus, and it did so by giving off 2 electrons. Loss of electrons is oxidation. Magnesium is oxidized. Or it went from 0 to 2 plus. That's an increase in charge, and we identified oxidation as being a situation where the charge increases. Not every reaction is going to move electrons. Here we were moving electrons off of the magnesium onto the iron. But sometimes the electrons don't move at all. If we go through the same process with this double replacement reaction, chlorine is a 1 negative, meaning that the copper in this case is a 2 positive. Sulfide is a 2 negative, sodium is a 1 positive. When we get to the other side, sulfur is a 2 negative, meaning the copper is 2 positive. Sodium is 1 positive, and chlorine is 1 negative. If we look at that collection, we can see that the charges don't change at all. If the charges don't change, it's because the electrons didn't move. And so when we look at this, that's not a redox reaction. That's redox at its simplest. The movement of the electrons is very, very obvious because of the changing of charge. Whenever you have ionic compounds involved, it's pretty easy to see whether the electrons move or not because we can actually see how the electrons impact the charge. The tougher situation is when the electrons are moving around kind of internally inside the molecules. When you're working with organic or biochemical situations, the movement of the electrons doesn't change these outward charges that we can see because molecules aren't made of charged particles, they're made of ions. But the movement of the electrons is actually kind of within the molecule between the different bonds as the bonds break and reform. So we need a way to identify redox reactions when they happen in that kind of a context. We're going to fall back on actually the historical definition of oxidation and reduction. Originally, oxidation was defined as the addition of oxygen because scientists didn't know about any of this electron movement thing. They just knew that there were a lot of things in the world that could pick up oxygen from the atmosphere. And so then they said these things are oxidized. Iron being one you're very familiar with. Rusting is an oxidation process for iron. And then reduction is the opposite, a loss of oxygen. And that kind of gives you an idea where those names came from historically, adding oxygen and essentially reducing the amount of oxygen. After scientists looked at a whole bunch of different reactions, chemists noticed that a gain of oxygen atoms often resulted in a loss of hydrogen. And so loss of hydrogen atoms was added to the list of ways to identify oxidation. And since reduction is the opposite of oxidation, it then followed that maybe reduction could be seen as a gain of hydrogen atoms. So we're going to go back and add that to our list here. So ways to recognize redox reactions. Possibility number 1, the charges change. Possibility number 2, oxygen or hydrogen move during the reaction. So we're on the lookout for reactions moving hydrogen and oxygen atoms around a little bit. So oxidation gets its name because historically it was a gain of oxygen. And reduction was its opposite, which represented a loss of oxygen. or a reduction in the amount of oxygen present. When they started to partner these processes up, they also figured out that gain of oxygen often went with loss of hydrogen, and loss of oxygen often went with a gain of hydrogen. So we essentially have three different ways to recognize when we have an oxidation reduction process. The electrons are still moving as we gain and lose the oxygen and the hydrogen. It's just that we can't see them because we can't see the charges. So we're going to use the hydrogen and oxygen to help us identify that the electrons have moved internally someplace in the molecule. In your textbook, table 8.4 does kind of a nice job of summarizing this for us. Oxidation always involves a loss of electrons. Reduction always involves a gain of electrons. However, you may have to sometimes recognize oxidation as being either addition of oxygen or loss of hydrogen. You may sometimes have to recognize reduction by a loss of oxygen or a gain of hydrogen if this isn't happening in an ionic compound situation and you can't track the charges, which would definitely be the easiest way of doing this. So you have to be on the lookout for all the different possibilities. So let's take a look at the hydrogen-oxygen situation. Combustion reactions involve the reaction of something with oxygen. So if I look at what happens here, my carbon goes from being with hydrogen to being with oxygen. So from the perspective of the carbon loses hydrogen and gains oxygen. That's the definition of oxidation. So we would say that the carbon in this reaction was oxidized. The oxygen, however, gains some hydrogen. And that's one of our various definitions of reduction, is to gain hydrogen. So if we track the movement of the hydrogen and the oxygen in here, we start to see that carbon is our thing that's oxidized and hydrogen is our thing that's reduced. Now, somehow in this whole mess, having identified carbon as being oxidized, that's the Leo situation. Somehow in here, the carbon has lost electrons in going from here to here. So this carbon has access to fewer electrons than that carbon. Hydrogen is reduced. It has gained electrons. So the hydrogen, in going from part of the methane to part of the water, essentially has access to a few more electrons. So the electrons are moving internally. You don't see any change in charge, but we have other ways to recognize redox reactions. That's really the extent of what you need to know about redox reactions for Chem 101. Like I said, they're really just setting you up for a biochemistry class, for a biology class, giving you enough of this vocabulary that you can go forward. At Oshkosh, Chem 101 is followed by Chem 102, which is organic and biochemistry, and this redox stuff is necessary to put into place to prepare for the biochemistry part of that. On the back here is a little bit of practice. I do want to change one of these reactions. So we're going to scribble this reaction out. And we're going to use a different one. I want you, instead of nitrogen reacting with oxygen, I want you to do nitrogen reacting with 3 irons. To make iron 2 nitride. And this is a solid. That first reaction was going to require the 4th definition of redox, which has to do with something called oxidation numbers. If you go on to take 105, we will look at that fourth definition using oxidation numbers. But we don't have to do that for 101, so we're going to get rid of the one that would require us to do oxidation numbers. So work with your partners. Work your way through 1 through 3. There's also a typo in number 3. Spell check got the best of me. That second one should be ethanol. Spell check knew ethanol. It did not know ethanol as a word, so it undid it and put it back to what it thought it ought to be. Okay, so work with your partners on some redox practice. I will work them up here, so if you get stuck, you can just pop your head up and see what I'm doing. Okay, practice time.
Can I go to the bathroom?
Yeah, make yourself a mess.
Okay. Do you rush on the second one?
Yeah.